All right, welcome. So today we're going to be talking about average atomic mass. And by the end of the day, we should figure out how the atomic masses on the periodic table are calculated. So the question is, why aren't the masses on the periodic table whole numbers? And the reason is every element has naturally occurring isotopes. And we've gone over this, but an isotope means that the atom has the same number of protons, so it's the same element, but it has a different number of neutrons. So it's the same element with the same number of protons, but it has a different number of neutrons in the nucleus. And when atoms have different numbers of neutrons in their nucleus, that gives them different masses. So isotopes are atoms of the same element that are different in mass. Each isotope has a mass close to a whole number because it contains a whole number of protons and neutrons. However, when we average the masses of different isotopes together, we end up with the decimal value. So how do they actually use isotopic mass to calculate average atomic mass? So it is a weighted average. Which means that it's calculated a whole lot like your grades are calculated. So in this class, your test grades count for 50% of your average, quiz is 30%, and then daily work is 20%. So what that means is test grades count more towards your average. They're weighted heavier and count more towards your average. It works the same way when we're calculating the average atomic mass. What we need to know is the abundance of each isotope in nature. So that's the percentage that it makes up of that element in nature. We have to take that into consideration whenever we're calculating the average atomic mass of an element. Isotopes that have a greater abundance, for example, hydrogen with a mass of 1, makes up 99% of all hydrogen atoms. So that means that that mass should make up 99% of the average mass for hydrogen. In order to do this, we have to convert the percentage or the abundance that we're given back to a decimal value. And the way that you can do that is divide by 100. Another way to do it is to simply move the decimal 2 places to the left. If you move the decimal 2 places to the left, it's the same thing as dividing by 100. We're simply changing the place value of that number. So I want you to think about a sample of an element in which we have isotope A and isotope B. And elements can have several different isotopes. It's usually not just 2 isotopes. Some of them could have 5 or 6 different isotopes that are used to calculate their average atomic mass. But I'm just going to go with the 2 isotopes so you can kind of see how the formula works. If I have isotope A and I know its abundance and I know the mass of that isotope, then what I'm going to do is take the decimal form of that abundance, so the decimal percentage, for isotope A, and I'm going to multiply it by the mass of isotope A. I'm going to do the same thing for each different isotope. I'm going to take the percentage or the abundance converted back to a decimal number and multiply it by the mass of that particular isotope. Remember that the masses of the isotopes are going to be different values, and so you'll have different masses here. You'll also have different percentages here. And again, there could be several different isotopes, but you would do that for each different isotope. You would take its abundance converted to a decimal value and multiply it by the mass of that particular isotope. And then we add all of those products together. So on the back of this sheet is an example. In this example, zinc has 4 different isotopes. So we have zinc with a mass of 64, zinc 66, zinc 67, or zinc 68. Zinc with a mass of 64 has an abundance of 48.6%. So that means that 48.6% of all zinc atoms have a mass of 64. And their actual mass is very close to 64, but it's not quite 64. We're going to be using the exact masses of the elements here in order to do this calculation. And so it's very close to the whole number 64, but not quite. That's going to make up half of our average because that percentage is about half of the sample. Zinc with a mass close to 66 has a percent abundance of 27.9. So a little less than a third of it has a mass of 66. And so we can see that we have the 4 different isotopes here, and each of them accounts for a different percentage of the total zinc atoms in the sample. So the first step we need to take is we need to convert those abundances, those percentages, back to decimal values. So for isotope 64, we had the percent abundance of 48.6%. We're going to convert that back to a decimal value. If I move the decimal twice to the left or divide by 100, it becomes 0.486. For the isotope with a mass of 66, it was 27.9%. And again, I convert that to a decimal value, 0.279. And I just continue doing this for each sample. Be very careful with abundances that have single percentages like 4.7. You still have to move the decimal over or divide by 100. And so 4.7% is going to become 0.047. So just be careful with those, because if your place value is wrong, then your answer is going to be wrong. And then 18.8% becomes 0.188. Once we've converted all of our abundances back to decimal values, then we need to multiply each of these. So the next step is to multiply each of those abundances converted to decimal form by the mass for that particular isotope. So the mass of isotope 64 was exactly 63.929 AMU. The next isotope was 65.9260. The next isotope was 66.9271. And the last isotope had a mass of 67.9298. We can actually do this all in one step in the calculator. We can put it in the calculator just like this. We can put the multiplication for each isotope inside of a set of parentheses, and then put an addition sign between sets of parentheses in order to add them all together. So that's what I'm going to do in my calculator right now. I'm going to enter this in. And there we go, it's all in the calculator. Now before I even hit enter, I do want to talk about something. Since we're averaging masses here, and all of the masses were in the 60s, before I even hit enter on the calculator, I expect my average to be somewhere between 63 and 67 or 68. My average should be within the range of masses that I'm averaging together. If I hit enter and I end up with a mass that's completely different, that means that either I forgot to convert a percentage back to a decimal, maybe I had the wrong place value, maybe I typed it wrong in the calculator, but there's an error. So make sure that you expect an answer that's within the range of the masses you're averaging. And in this case, I got 65.3792241, which is definitely within the range of masses that we're calculating. The other thing we need to look at is significant figures. So just look at the masses, not at the percentages. And if we look at each of the masses that we were given to average together, this mass here only has 5 significant figures. All of the others have 6 significant figures. We're only allowed to keep the fewest number of significant figures in our calculation, and so we're going to keep 5 sig figs in our answer. So that means I'm going to round this answer to 5 significant figures. I'm going to keep the first 5 significant figures, 65.379, and look at the next number to round. Since the next number is a 2, I'm just going to keep it the same, and it's going to be 65.379 AMU. So I hope that clears up average atomic mass calculations, and I hope that this helps.